All right. Uh, Hello and welcome to this seventh episode of You Wouldn't Type Check a Car. Uh, like I was saying on Twitter the other day, I'm really excited to get back into a regular schedule for streaming. So I'm trying to make sure that I'm doing this at least every Saturday while I have the time. I'll probably get busier again in the semester. I have to take a class this semester, and also there's a bunch of travel lined up. Mainly for Build It actually. I'm gonna be traveling, giving away, making some workshops and tutorials around. So I might have to skip some weeks in the middle of the semester, but I'm gonna try to be very regular on this stream. I think I want to quickly get through this NES emulator stuff, and then we'll do more fun, more I guess low level system stuff. Optimizations, writing low level high performance code, writing some compilers. It should be fun. But also, first things first, I guess. Second things first. I finally figured out how to make followers only emotes. It wasn't working for some reason before, and I could only make subscriber emotes. But now you can, if you're a follower, you can actually use the build it emote in the chat. So if you just say AJAYCXX, AJAYCX build it as an emote, that should throw the build it emote in the chat. So hey, we have build it emotes now. Maybe I'll make some more later. But yeah, I have finally figured out how to use follower only emotes. Okay, so yeah, let's get back to where we were last week. I actually have a arm pain in my hand right now because I went to the gym yesterday after a long time, like after I want to say at least a year, maybe more. And I did some curls and stuff, and my arm really hurts. Like my forearm really hurts. But it's fine. I can type. It only hurts when I like try to make my arm straight. Like if I do this, it hurts. But hopefully it shouldn't interfere with today's work and me trying to type on the keyboard. But okay, so let's get back to the simulator. I'm gonna change the scene. I'm gonna look at some code. Oh, yep, this is what happens. Okay, just gonna bump up the font a little bit. Yeah, so last week when we were working on the emulator, the thing that we left off at the end was this bug that we were having where Build It was sort of generating or jumping to an execution that was outside the address range. And the reason it was happening was if you actually let's just run it. This is when I'm running the Super Mario Bros. ROM, by the way. Yeah, so it jumps to this null instruction and execution stops there. The reason this happened was it was jumping to this address FFF0. Now, FFF0 is not a valid address. There's no instructions there. It has data there because the whole ROM is loaded, the program ROM is loaded at this address, but it's not supposed to have instructions at this location. It just has some vectors, basically, like reset vector and some other vectors at this location. So this is a bad instruction. So why did we jump here? Turns out that jump was from this 7F93 location, which also is a bad address because our whole program starts from 800. So why did it go to 7F93 in the first case? That happened because 7F93 has there's a relative jump in the first initial part of the program, which is somewhere I think here. Yeah. And this relative jump basically is always supposed to not be taken, but somehow it gets taken because we loaded the long value, and that's what was jumping to this address. And from there, it all just doesn't make sense. So why did this happen? We were debugging this the last time, and we realized that this is a branch on positive. So the last value that was loaded was this LDA-ABS. And if this is a positive value, it's going to take this jump. If it's a negative value, it's not going to take the jump. So what is this address? We checked it was like 2002, which technically should be uninitialized memory in this because we haven't written to this address before. But turns out I debugged it a little bit more, and I realized that 2002, actually the whole 2000 to 2400 range, is actually mapped to the PPU. So what is the PPU? The PPU is basically the picture processing unit. So if you actually know about these NES game systems, they have a main processor, which is this MOS 6502, which we are emulating. And it also has a coprocessor, which is a picture processing unit. So the picture processing, hey, how are we doing today? We're doing great. We're getting back on the NES emulator stuff. Yeah. So what I was saying is, what was I saying? The picture processing unit is basically a coprocessor that takes care of actually rendering the pixels on the screen. The main processor basically moves a bunch of data, which is the sprites and the positions of the sprites and actually some raw pixels into the picture processing unit memory. And the picture processing unit basically runs in a sync with the main processor. The clock cycles are synced, and it sort of every cycle it draws a bunch of pixels on the screen and keeps moving ahead, like in a row measure way. And that's what draws the image on the screen. And these are like these are for the CRT technology, the CRT monitors that we had before. I guess you could still make it work with LCDs, but that was made to work with those CRT monitors. So the problem is we are currently not simulating the PPU properly. Which means if we read some values from the PPU memory or from the PPU registers, it's going to give us garbage values. In fact, it's going to give us uninitialized memory because we treat of that 2002 as just a normal address, and we have callocked the whole memory, so it's just going to give us 0, which means that branch on positive is actually going to be taken, and that's going to jump to the wrong location. So I guess the first thing we need to do is to fix that. But before we actually do that, I wanna make sure that this never happens again. So like I wanna make sure that we never jump to an address range that's not valid program address. I know it's hard to determine what the valid program address range is, just because you could technically just write instructions anywhere and execute them. But we're not really supporting that right now. Like we're not supporting changing instructions on the fly or creating instructions on the fly, mainly because we have this compile execute loop. So it's hard to do that. We're assuming that the program never changes, and that's true for most of the ROMs, so that's okay. So what we're going to do now is we're going to keep the bounds of the instruction pointers basically within the program memory, and if it ever tries to go out, we're going to insert like a dynamic jump in a dynamic error into it saying that, hey, you were not supposed to jump to this address, I don't know what these instructions are. Rather than misinterpreting them, I'm just going to fail. So okay, so let's start working on that. So mainly what we need for that is in our emulator, in our emulation context, I guess it should go in the, no, it should go in our execution context. Let's see. In our execution context, we have actually in the pipeline. Yeah, in the execution context, we have our program offset, we have our main memory, and we have our D main memory. These are basically the same, but just one we use to refer to the program and one we use to refer to the data. Yeah, it could be different if the program is sort of like we're emulating a system that has a separate program memory and a separate data memory. So we are doing this differently. Okay, so what we're going to do is we're actually going to make two variables called program offset lower and program offset upper. These are going to be the bounds of valid addresses where we can jump. And these should be set exactly where our program offset is set initially. So that happens, I think that happens in the attaching the ROM. So that should be in source pipeline. Yeah. So we have the attach ROM, right? At this point, we basically set the program offset here. We should also set the program. Okay, so this is where we actually copy the program in this particular mapper. So in the case 0, we copy over the instructions into the right memory location. We should set the address ranges here. So what we're going to do is program offset lower equals, for this specific mapper, we are mapping it between 0x8000. So we can never go below this, and program offset upper is going to be C000 plus 4K. I think that just comes out to be 0xFFFF, if I'm not mistaken. Yeah, this is like the inclusive bound. So we could also actually just make it, wait, what's the type for this? It's NES word. NES word is just 2 bytes, right? emulator.h. NES word is unsigned short, so it won't be able to hold bigger. So okay, let's just make it inclusive. So these are the only valid addresses that we can jump to. So anything lower than 0 at 08000 and anything higher than 0xFFFF, we'll ignore that. We'll not treat it as valid instructions, and this will actually help us debug better. So going back to our emulator, which actually generates the code for these things, what we're going to do is, okay, so we have our main loop, which just jumps through all the instructions and interprets them. But because it's written in builder, it actually generates code instead of executing it. So before we do anything, before we even touch the opcode, we're going to check if this lies within our bound. So we're going to say if PC, which is a static variable in this case, and so is the offsets. The offsets are known statically. So we're going to say if PC is less than program offset lower, right? Less than or less than equal to less than 8000 is a valid address, or PC is greater than XFF is a valid address. Let's say so. Let's say greater than. You can say program offset upper. At this point, we're going to error out. So we're going to error out in the same way as we did before, which was with the default case of a bad instruction, which is just say runtime unreachable, jump to invalid instruction. So this runtime unreachable is actually going to produce a function call in the generated code, which stops the execution. So this is not going to stop the compiler. The compiler is still going to continue. If it jumps to this address, it's going to go back and do more things, but it's going to fail at the runtime. So this will only fail if we actually take this jump. While interpreting, we might take this jump based on, like, say, a relative jump or anything like that, but it will only fail if we actually go to that address at runtime. And that's the power of how build.it is written. We can explore all paths without having to actually fail on those paths. Okay, sorry, okay. So instead of saying jump to invalid instruction, we're gonna say jump to invalid address, and then return 0 so that the execution stops, and 0 tells the outer compiler that hey, I'm done interpreting, please stop. This also actually will never reach, like return 0 will never reach, because the function unreachable just exits. But we have to still put the return here so that the compiler can stop. The compiler needs to know that I'm not going to execute anything more after this. So that's why we put a 0. I'm going to just put a comment here. Make sure that we are interpreting a valid address. Okay, so this way, now the code that we generate will always only generate code for stuff that's within bounds. Okay, program Lewis. Yeah, I think I didn't save this. Oh wait, emulate code is not in the context. It just takes it as a parameter. Sorry, we need to change this. Actually, why is emulate code not a member function? Right? This should be part of the pipeline. I guess that's okay. This the only one who I've seen who likes light mode. Yeah, there's a long story behind that. I used to use dark mode before. What happened was, as I started working at different times, like I used to switch between working during the day and also working in the night. And when I was working at night, I used to work at home in my bedroom, like in the dark. The dark one actually makes it very hard for me to read stuff on the screen, especially when it's like too dark. Like the font, if it's too thin, my eyes can't see it properly. Like I see it very blurry. But if it's like a dark text on a white background, then I see it much more clearly. And I don't want a complete white background either, because that hurts my eyes at night. Like if I'm working in a dark room, then it's gonna hurt my eyes too. So I have settled on this like sort of a yellowish cream color shade, which I think works in both the cases. I could have different profiles based on different times. Like I could change it based on times. Have a more sort of dark profile, I guess during the day, and then at night switch to something like this. But uh, I think for now it works for me. And I know some folks have said that on the stream, my screen actually hurts their eyes. If that's too much of a problem, actually let me know. I'm happy to. I have a profile. Like I have a terminal profile that here Ubuntu Black that has a dark profile, and I can use this if needed. But I'm gonna stick with this right now. It's just easier on my eyes, and I'm too used to it too. Okay, so we also need to actually pass the offsets, just because this is not a member function. We could wrap it inside. We could just pass the context object, and it might actually work. Should we do that? Yeah, let's do that. Let's just wrap this whole thing in execution context. So that way we don't have to pass anything. And then we can make members inside to just like not have to change the code. This needs to be an argument still, because this comes at runtime. So DNS byte adder. This is a runtime parameter, so this needs to be separate. This cannot be part of the struct. So this doesn't need to be here, and then NES word offset equals to ctx dot offset NES word program offset lower equals to ctx dot. Okay, and then what we can do is change this to accept the execution context t ampersand ctx, which means we also need pipeline.h, and I hope pipeline.h doesn't need this. It needs emulator.h. It's okay. It only needs .h. This needs the dot. Should be good. Yeah, this should be fine. Okay. And then we also need to change pipeline to change the way it's called. So get program offset. Here we need to pass the context emulate code. Yeah, instead of this, we just need to pass the address now. So start this. Okay, let's see if this works. That preference, that's preference, whatever suits you well, you can use. Yeah, I've settled on it over a long time, so I'm not planning to change it soon, for myself at least. I tried it recently. I just started switching to dark mode to see if it I'm better with it now, but I'm actually not. So execution context T was not defined in this scope. This is the problem. Okay, emulator.h needs this. Emulator.h is required by pipeline. Why does it need an emulator actually? Doesn't, right? Oh, for the types. Okay, you know what? It's easy to handle this. We're just gonna, since this is just a declaration, we can do struct execution context t. We have to have a forward declaration somewhere, so why not have it here? Actually, on video, the light mode is readable, then it seems. Yeah. Okay, has no offset. Yeah, let's program offset. Ideally, I should just move the whole thing into pipeline, including emulation. But yeah, the type def should probably move to a separate header to say types only, and then those should both be included by pipeline and header. That would make it the cleanest. But I think this is fine for now. This is not context. This is program offset. Also, I was mentioning before that now you can use the build it emoji emote in the chat if you are a follower. So AJ:AJAYCX build it. You can use. I finally figured out how to make it work for followers and not subscribers, which was okay. Let's see if this now fails early. Okay, so yeah, exactly. Now this time it doesn't go to that bad address. It generates code for 7F3. Actually, it doesn't generate code for 7F3 now because it just puts invalid instruction jump to invalid address at that location, and when the execution reaches there, it just complains. So that's good. This is what we wanted. We're not going to like keep on jumping arbitrarily now. If you go outside the bounds, we're gonna stop. It's good. Yeah, that's working. So that's good. Okay, let's go back to fixing the PPU issue. Let's so the way actually let's pull up NES wiki and NES wiki, NES dev wiki, that's what it's called. We need to read about the PPU a little bit before we get into this. Okay, so reference guide, PPU. The PPU is actually surprisingly more complex than the main processor itself. It does so many things. Yeah, but one of the things that we need to know is its registers. So here are the registers. I'm gonna bump the font a little bit. Okay, so the PPU exposes 8 memory map registers to the CPU. These nominally sit at the address 2000 to 2007 in the CPU's address space. So the CPU, when it addresses these locations, it actually reads those registers instead of reading its own main memory. But because their addresses are incompletely decoded, they are mirrored in every 8 bytes from 2008 through 3FFF. So basically the same address, the same value 2000 to 2007 are basically copied over and over and over again to 3FFF. That's a large space. For example, a write to 3F456 is the same as the write to 2006. And the reason it's done, I think, at least from my understanding, the reason it's done this way in the hardware is you can now, okay, so how many values those are? Those are 8 values, right? Which means you can only look at the lower 3 bits to figure out which register to access, even if you have a larger space of memory. So you need to check the higher bits to make sure that you're in the right range, but then you can skip over the middle bits, which saves some wires and saves some transistors on the chip, and that's why they do this, I think. Yeah, that's what it means by, but because their addresses are incompletely decoded, like they're not completely decoded, only part of it is decoded. Okay, so we can implement this. We can make sure that we can only look at the lower 3 bits, and that way we'll be fine. Okay, so after power on and reset, many of the PPU registers are not immediately usable until enough time has passed. See, so this is fine. I think this is fine. We can implement it in a way that this can immediately be initialized. Like there is no reason that it shouldn't be immediately initialized. But okay, so these are the 8 registers that it has: PPU control, PPU mask, PPU status, and 2002 was that address. This is the address you are invalidly reading, and it has a bunch of values. So they have it explained, everything down, but yeah. So PPU control, PPU mask, PPU status, OAM ADR, OAM data, PPU scroll, PPU adder, PPU data, OAM DMA. We will come to all of these, what they mean, and we'll implement them correctly. But first of all, what we need to implement now is some sort of this memory mapping. which means if the CPU loads an address, we have to first check if it is one of these addresses or if it is one of these ranges of addresses. And if it is one of these ranges, then we need to sort of do a special execution of that code, and not just execute it, not just read memory from the data from the memory directly. So this basically means we have to change the way data is loaded. In our entire code, there's a few places where data is loaded, at least in the generation side. So for example, when we say load byte, right? Load byte is one of those functions that generates. Oh, come on. Yeah, so load byte is one of those instructions that, based on different addressing modes, loads the address. But this one I think is mainly used for instruction memory. Actually, never mind. It also does D main memory. So what we need to do now is actually make this into a logic that first checks if it's in that range, and if it's in that range, calls a special function. Otherwise, it directly loads from the memory. The problem with that is if I just put a condition here, like if I change this to say, let's see where it's loading. Yeah, here it's loading something from this, right? So I could change this to say if this address, right? So like say context dot xreg plus adder plus 1 is greater than 0, like this, and less than like 0x400, where it's map, then do something else, like then load it differently. The problem is it's going to generate a lot of if conditions in our code, and the thing is they're not going to change. They're always going to be exactly the same. So why do you want to generate the same thing over and over and again? What we can do is just make that into a function, a runtime function that just takes an address and gives you the value of that location. And that way we can abstract all the changes for the load address into that sort of special function. So we need to implement that first. Which will allow us to control the loads. This is not the only place where it's being loaded, by the way. So if you look at this D main memory, these are a bunch of loads. So everywhere there's a D main memory of something that's a load. Let's see actually how many do we have? Because we'll have to change all of them. D main memory off. Yeah, I should have put this into an address beforehand. But not all of these need to be done that way actually. So some of these, like for example the 0 page X, it's guaranteed to always be in the 0 page. It's always guaranteed to be in the 0th page. Now the 0th page can never be mapped to the PPU, so we can do a direct load on that. Only a few of them need to actually be changed. So we will take care of that. Yeah, these indirect ones basically also load the address from the memory. So there's like a bunch of loads there. All of those loads need to go through the special check. Okay, let's do this. Hopefully they are all inside this load byte and store byte. Same thing needs to be done for store, by the way. If there's a write, then that write needs to go through the check, special check. Okay, this also has a few loads directly. We will fix them too. Okay, it's just gonna be a bunch of work. Okay, so first of all, what I'm gonna do is make a function that actually loads the byte from the address. So let's say static DNES byte. It's gonna return a byte no matter what. Load byte adder. So this is gonna return. It's just gonna take an address and return the value at that location. This address is also going to be dynamic. Like we're not going to know this address at compile time. It's only going to be at runtime because it could be in a register, it could be in memory. So yeah, we're gonna make it DNES. The convention we are following is anything that starts with D is dynamic, which means the code, it generates the code for that rather than executing it in the compiler. Okay, so it just takes an address and returns an address. But we also need the context for this because the context has like hooks for like the context has other things like the register state. It also has, I mean, we probably don't need the register state for this one, but like where the main memory is, and eventually we'll need like a handle to the PPU, so all that needs to go here. Okay, so DNES load byte adder, NES context T, DNES word adder. So in this we will just call the runtime function. So let's put that here. build it in var. So we just want to call that external function which implements the whole logic. I'm going to change this to be NES byte and NES word. Let's see. Actually, do I need these runtime prefixes? For printf, let's keep it. So I mean, it's in a special namespace, so it's fine. But let's say load byte equals to builder as global runtime underscore load byte. Okay, so this thing is going to accept. It's going to accept a bunch of things actually. But we don't have to change that. This is okay. We can actually just keep this void. Okay. Because builder doesn't type check function calls. It just inserts a call no matter what arguments are. We rely on the backend compiler, the compiler that actually compiles the generated code to type check this. So that's fine. We don't have to worry about it. Okay, so we have the context and we have the address. So we're just gonna dispatch this. So we're gonna say return runtime colon load byte, and we're going to pass ctx dot d main memory. It needs to know where to load from if it doesn't like belong to that range, and the address. So for now we just pass these things and it will return the value. In the same way, we're gonna make another actually the store doesn't return anything. So static void store byte adder, same stuff again. But this time it's also going to take a value. So dnes byte value doesn't return anything. Runtime load byte ctx.d. Okay, so these are just going to dispatch function calls. Okay, so now we need to start replacing these everywhere. Okay, let's go line by line. We have load bytes, right? So okay, so this one loads from the context and returns the value at the address. It is an ABS, which means it could absolutely be any address, which means this needs a check. So we're going to return load byte adder context comma adder. Adder is just the parameter we had here, so we're just gonna send that in. This can go away. Okay, return. Yeah, this is going to be a little bit painful. I could do a find and replace. I'm just not exactly sure that I've done it correctly. You know what? We can. Nah, I don't want to mess it up later. Let's say I could do a nice regular expression that takes the parameter inside the square bracket and then replaces it as a second argument. The problem is we have to check if it's a load or a store. I don't want to call load where there should be a store. Load byte adder context dot. These are all. Oh, actually, no, wait. This is zero page. So zero page doesn't need this. Sorry, this was fine what it was before. Like I said, zero page is always going to guaranteed to be in the zero page, just not the PPU memory. So we don't need a special check here. It's good. It saves a bunch of runtime checks for us. Not gonna lie, Vim in light mode looks great, right? Right? It looks. This is such a clean. I'm using this skin, by the way. So when I was trying out dark mode, I was changing it. I was using desert before, but this one I think is just brown, like some highlighting, and the other palette highlighting is I think default. Some special highlighting for C++. No, I haven't changed it. This is the standard syntax on highlighting. I've tried different things before. I'm happy with what I have here. So anyway, going back to for emulation. Okay, so zero page is fine. This one we change. Y also needs to be changed. So this becomes text comma context dot yrect plus adder, right? Okay, so this is AMZPGX. What does this do? It takes xrect plus adder and then dereferences it. The thing about this is, what is adder here? Yeah, adder is the instruction of 0. So it takes an offset, adds it to x and dereference it. But this is not guaranteed to be in the 0th page. Let's actually look at our manual. It's on the readme. Material. Oh, it's already open for some reason. Okay. Addressing modes. Context spelling wrong on line 54. Thank you so much. 54. Save me a bunch of debugging later. Okay, addressing mode. So here the addressing modes, I think we're looking at we're looking at 0 page X and yeah, 0 page X is the one we're looking at. So that would have been a nice Twitter thread for later. The spelling error for context, or me ranting about dark mode. I don't know, either, I guess. Okay, so you have index and 0 page index. I think this is the one that we're looking at. Index and 0 page index. In this mode, the address is given and added to either X or Y index registers to give you the actual address of the operand. Note that the different operation codes determine the index registers used. In the 0 page version, you should note that X and Y registers are not interchangeable. Most instructions which can be used with 0 page indexing do so only with X. It doesn't say anything about the implementation of it. Here it is. In these modes, the address given is added to the value in either X or Y index to give you the actual address of the operand. The different operation codes determine the index registers. This is just the encoding. Pre-indexed. Where is the description for the 0 page version? Oh, I think it is this one. Yeah, okay, this is the one. Pre-indexed indirect. Oh, okay, yeah. In this mode, a 0 page address is added to the contents of the X register to give you the address of the bytes holding the address of the operand. The indirection is indicated by the parentheses in assembly language. You know what? Let's just see an example of which one. I think this might be different. 0 page X. Which instruction uses 0 page X? And let's do this properly. Include instructions. Yeah, so we have our CPGX am underscore CPG underscore X. Yeah. So there are a few instructions like and uses CPGX. Okay. So well, let's look at its opcode. Okay, and here it is. So it has 0 page X and opcode 35. Right? Is that 35? $224, 187. Think so? Oh. Oh, it's 35 in hex. So how much is that? Touching something here. what am I doing? 0x35 is 53, and then we had 224 minus 187, which, what? Because I was looking at the different one then. So maybe 187 plus 187 plus 53 is, come on, 187 plus 53. I forgot this is not PC. 240. Let's look at what 240 instruction is. Yeah, okay, it is AMZPGX. Okay, this is the right one we're looking at then. Okay, so okay, addressing mode CPG X. I think it is this one. 0 page indexed. In this mode, the address is given is added to the value in either X or index register. Okay, so it's not gonna be in 0 page because it just specifically says in these modes the address is given is added to the value in either X or Y index register to give you the actual address. So it gives you a 0 page index, like it gives a single byte value for the address and then adds X to it, which could go out of the 0 page. So this means we have to use our special load function here. Yeah, I was just making sure that we're not inserting a special check where it's not required. Okay, load byte address, context plus xreg address. Okay, and this one definitely needs it. Like these are complicated. So no, actually no, this one doesn't need it. They need it because after the computation it's swapped modulo it's modulo's 0xff, which means it will be in the first page. Okay, so this is good. You don't need to change this. Actually change this. Okay, yeah. Same for the low. So these two addresses are always going to be in the low in the first page, but not this one. This could be anywhere. So return load. Hopefully we don't have to change a lot of things because we have abstracted away our load from the addressing modes already into these two functions. So we don't have to make the change for every instruction except for some instructions that do manually change it. Like do have a manual load in their implementation because of like say a push or a pop on the stack, something like that. Okay, these are also fine. These are wrapped around to 0 page, so there's guaranteed to not have a problem. Where's my okay, let's go to this one. Yeah, this load needs to still be changed. So return load. Hopefully the stores will be easier because we can just look at what we did for the load and then wow, I really cannot spell context today. Wonder what happened. Okay, so it's good. Rest are fine. Okay, so load bytes here are good. Let's do the same for store byte. Okay, this is only stored into the instruct register. Okay, this is the one that we need to change. So this becomes store byte adder context comma adder comma data. This is 0 page, so I'm going to change this. This is absolute, so this needs to be changed. Store absolute y also needs to be changed. This one we just check needs to be changed. So These first two need not be changed, but this needs to be changed. So actually those are even loads, those are not load stores, sorry. I'm just going to copy this. Okay, so these are done. Now let's change the main memory. Any sort of like manual loads inside the instruction also needs to be changed. So for example, yeah, this is like a break instruction which pushes things on the stack. Technically the stack is never guaranteed to be on the PPU. Like who in their right mind would change the stack pointer to point to a PPU like mapped memory? But you know, in the spirit of being complete, we're gonna do this properly. I don't know, man. We need to emulate things properly. Okay, so this goes away. This is also a store. So store byte address context.sp status. Okay, this is loads. These are guaranteed to be not mapped, so I'm not gonna change this. It's loading basically a interrupt vector and then jumping there. I know this is guaranteed to not be in the PPU memory, so I'm not gonna change this. Okay. We could actually even read this from main memory. Like these addresses do not have to be dynamically loaded, but I want to leave it to like if the program sets up the interrupt vector later, we do want to be consistent. So these are fine. Let's go to the next one. What is this? Jump. Okay, yeah, jump has an indirect load, so that needs to be done properly. Okay. These are again stores for jump to subroutine. So when you jump to a subroutine, you push the addresses to the return address on the stack. So that needs to be also, again, the stack will probably never point to these special addresses, but we'll do it the right way. And these two can go away. Cool. Oh wow, there's a bunch. What is PHA? Push the accumulator on the stack. Okay. This is PHP. What's the difference? Oh yeah, pushing the status on the stack. Sorry. Store byte address context. Okay. This is pull from the accumulator from the stack, so it's the opposite. PLP is probably the opposite of that, so I'm just gonna do this. Wait, what did I do? Continuous byte status equals. and RTI, return from subroutine, no, return from interrupt. Sorry, this is taking a bit because I did not think about this correctly before. Like I should have done all loading and storing through a single function, but foresight, I did not have the foresight for this. And these are also loading the return addresses. So okay, this goes away, and RTS, the same as this, so I can, oh, just copied the wrong thing. Can I copy it from RTI? Yeah, I think it should be the same, right? Yeah. Perfect. Is there any status in this? There's no status. Great, we are done with dmain memory, finally. So the only references to dmain memory now are for the 0-page versions, which are guaranteed to be in the 0-page, so everything is great. Okay, let's compile this and see what it generates. This should generate a load now. One error only. That's good. Great, it runs. Now when we try to run this, obviously it's not going to run because we haven't implemented that function yet. Like for example, implicit declaration of runtime load byte, it says that this function doesn't exist, but we can look at the code. Let's see what it generated. So here we go. So for every load now we have this runtime load byte. Is this more expensive than actually doing a load? Depends, because we're going to write this in the header, so it gets inline always, which is good for us. That way we don't have to implement, it'll get inlined if it knows that the value of the address is not. So for example, here's an example, right? We do var17 equals to 8194. And now runtime load byte checks if var17 is within a particular range, right? It knows, like if it inlines this correctly, it knows that this check is not required. And the backend compiler will handle sort of optimizing this for us. That's what you're going to rely on. Like backend compilers are smart. Like C compilers are smart. They do a lot of things, and we will leverage that here so that we don't have to manually implement this. The reason why we couldn't do this optimizations ourselves was because this was from a different, I mean, we could do it. This was from a different instruction that we were emulating. So now we would have to like basically keep track of in our compiler, keep track of like constants that are in registers and then check. And we could do that, like that could work. But if the backend compiler can do that for us, why repeat optimizations? I do not believe in rewriting the same thing again and again. So yeah, this is good. We don't need to, we just need to implement these functions now. So in the most default case, that's just going to load from the memory. So let's say it's going to be in runtime.h. Yeah. So we're going to say static inline because we want it to be inline if possible. Runtime underscore load byte const char star. Is it okay if it's const char star? Yes. Memory and const unsigned short adder, right? But we also need for declaration. So in the most default case, we're just going to say return memory of adder. And in the same way, for the runtime store byte, we're going to just write it. And then we will add checks on this. On this one takes const. Oh, this time the memory cannot be const. Const unsigned char value. Actually, this needs to be const unsigned char. And it returns unsigned char. Okay, this looks fine. So we're just gonna do adder equals to null. Okay, so with this change, our function should work exactly like before. Too many arguments to function load byte. Ooh, we inserted a load byte where there should be a store. Damn it, this is a problem. Is it load byte adder, right? Two arguments, two arguments, two arguments, two arguments, two. Huh. Oh wait, maybe I didn't change the function name. No, both are sysbyte. Store byte. Oh, it's calling store byte address is calling load byte. So that was causing the mistake. Okay. Yeah, this is what I meant by like we let the backend compiler type check it for us. Like technically the compiler could itself complain saying that, hey, your function expects 2 arguments, why you're passing 3, but we don't type check that and build it. Okay, here we go. So it ran the exact same way that it was running before, where it jumps to a special, like the load is normally done. And now we can actually start inserting checks into it. So let's go to the runtime.h and first let's say, actually let's define static bool is ppu adder, right? And const this check needs to be you know what, let's call it something else, not just ppu address, because there's going to be other mappings too. So is mapped adder, right? So it's going to say it's mapped to something else, not the memory. Constant sign adder, and for now it's just going to be if adder is greater than 0x200. What's the range for ppu? 2000 to 3fff. So 2000 greater than equal to or address, and address is less than 0x4, right? 3fff4, yeah. Then return true, return false. This is C code, by the way. This is not C++. So depending on the version of C you're using, it could support it, but anyway. So okay, so for the first one, we're just gonna say if is mapped adder, we're gonna just print a message for now saying printf attempting read from address equals percent, what is short, 0 to no 0 4x, yeah, 4x. Okay, and it's still going to return the same value, and then we will change this later. Okay, so look, now it said attempting write to address 2000 and attempting read from address 2002. So we know that now we are trying to actually do reads and writes on the PPU. So now what we're going to do is in the runtime itself, we're going to have a special function that handles everything that's related to PPU. So we are going to make two functions called handle special writes, which are not going to be implemented as headers, but like separately in the PPU. And then we will dispatch the load to them and store to them. So technically we also need to pass the arguments for the PPU, but we can do that here. That should be fine. Yeah, that should be fine. Okay, so let's say inside char handle PPU load. So now we need to actually create a PPU type that as a runtime PPU type. Our entire PPU is going to be runtime, by the way. There's no code generation for it, so that should be okay. So in runtime ppu.h. If not defined, ppu.h, but runtime ppu.h. And we also need to make sure that it's not compiling it as, because we also link the runtime into the code for testing at least. Actually, no, not just for testing. It's called this header is included inside the runtime because in the compiler, because it whole runs in the same process. We're not generating code separately and then running it. We are basically, it depends on how we compile it though. It's okay. It doesn't hurt to have. We never compile this as C++ code, but it's okay. Okay, so inside this now we're going to have the PPU struct, which is going to be currently just a PPU instance. Let's keep it empty for now. This will have all the runtime PPU state, including its registers, including its memory, and everything. And now we're going to implement these functions. So handle PPU load goes to this. So this becomes if PPU instance handle PPU load. This is going to take address for a PPU instance, and it's going to take the address. So unsigned char, no, not char, unsigned short, right? And in the same way, we're going to have. We could also inline this, but doesn't need to be, because this is only going to be get called when we actually have a PPU address. So that's okay. It doesn't hurt our performance so much. I mean, modern processors are powerful. They take care of this anyway. We are emulating a processor that's like 50 years old, so it's okay. It's mostly going to perform fine. Okay, so these two we need to do, but what this means is we also need to pass these PPU addresses to PPU PPU instance to this load runtime load. So what we're going to do now is wrap everything that's at runtime into a runtime context. Sorry, there's too many contexts here, but it's required. Clean abstraction. So we're going to make a struct NES runtime context, and currently it will just have a pointer to a PPU instance. So struct PPU instance star PPU. Okay, and what you're going to do now is these are going to expect it. So NES runtime context star CTX. Thankfully, we don't need to change this in every single call because we have wrapped that into a runtime, like in a compiler function. So we can just change that at one place and everything should be fine. This I thought about a little bit ahead. Okay, I'm gonna make sure that these are properly indented. Okay, so this is good. Time load byte is mapped address. Runtime context. Okay, so now we can just, instead of doing this here, we can say if return handle PPU load, and it's going to take CTX of PPU, comma. Oh, so this doesn't need memory, only needs this. Okay. And this can go away. And this becomes to handle PPU store CTX of PPU error value. And so it doesn't overwrite it. Okay. Yeah, this is good. Now we need to change the calls to actually pass this runtime context, but before we do that, we need to create that context. So we need a special type for it. So we're going to create what is called a name type in BuildIt, which is very easy to do. So we have extern const char star nes runtime t name, and we're going to create a type with this. So type def builder var of name of nes runtime t name. That's a bit long. Actually, we don't need a special type for this because this type never get used. You're never going to declare local variables of this type, but it's okay. It doesn't hurt. Type def builder dynamic var name nes runtime t name. And this becomes tnes runtime t. Yeah, so we have created type def for holding this, and now we are going to I just need a pointer for this, right? So let's make it a pointer. Runtime ptr, yeah. tnes runtime ptr runtime ctx. Okay, so now it's holding a dynamic pointer to a uninitialized pointer in this case. We're just going to say null ptr for now. Actually, no, it shouldn't be here. Okay. And when we create the context, we will set this properly. So in the emulator, now we can pass ctx dot runtime ctx as a parameter. And let's just check if this works correctly. It's probably not link, but should compile. Oh wow, lots of errors. Let's see one by one. First, one by one. Okay, builder name. Yes, it should be builder name, not name. Handle PPU load was not declared in this scope, yes, because we did not include the header. Does this need to have runtime? Oh no. Let's see. Actually, it should have been pipeline. What are the flags we are actually passing? Yeah, we are passing just runtime. Okay, so we are passing the runtime directory. So this just needs to be great. 52. Function is not supposed to return anything. Okay, great. I think this is compiling now. Spoke too soon. Unknown type. Oh, PPU instance. PPU instance? What do we call it? PPU instance. Yeah. Oh, struct. It's gonna take a while before we actually implement this PPU. NES runtime context star. Known type name. NES. Oh, again, struct. Great, and it's all that's missing now is runtime t name. Okay, so that goes in emulator.cpp. It compiles. Okay, let's try running this. Something about loading compile module failed. So this is the first time I'm seeing this. A load is failing. Interesting. Did it even run? Oh yeah, it has a linker error. Yes, obviously it has a linker error because when we haven't implemented those functions yet, right? So yeah, that makes sense. Okay, so let's say let's add those functions to ppu.cpp. Wait, ppu dot what is runtime.c, right? Yeah, so ppu.c. We need to implement those functions, right? So now include ppu.h. Just like runtime, this should be, yeah, this should be fine. I'm gonna open that for, yeah, and these functions need to be implemented. These are gonna be empty functions for now, so this is gonna return 0 and this is gonna do return. We need to add this to the make file. Runtime objs. Great. Let's see if this runs now. Segmentation fault. Why is there a segmentation fault? There's only one way to know. Last week I very famously said that segmentation faults, I'm happy with them. Now let's see if I can actually do that. Oh, we never added any debugging code. Okay, give me a second. I need to add some flags. Okay, so we have C flags here. Let's do this. I'm just gonna say, well, these are for the compiler. What about for the execute function? That actually should be part of the pipeline. Here. So what I can do is I can change this to just have -o0-g. That way the code that we compile for the runtime will always have debugging on it. There we go. Handle PPU store CTX. Oh yeah, we never initialized the CTX, so it's null. Come on. I'm gonna switch this back. So the easiest way to do this is to allocate memory for it. How to do that? Are we gonna do it through a global function? Are we gonna do it through a how are you gonna do it? Global variable or communicate through the execute function? I think we can just pass it as the execute function. Okay. So we need to think. We need to set. So in the pipeline, we need to first create a NES runtime and a PPU. So run main loops does init regs and everything. Does execution context have? No, currently don't have that. Should we get it somewhere else? I guess we could have it inside the init function for it, right? Yeah. So the constructor for emulator can have it. Actually, we can just, no, it cannot be local to the run main loop because the run main loop, yeah, it can be local to the run main loop, yeah. So let's just do it here. I'm talking about where do you actually create the context, the runtime context. So I'm just going to do it here. I'm going to say NES this has runtime.h, right? Yeah. So NES runtime context, runtime context, and then it's gonna have NES PPU instance PPU, and now runtime context.ppu is it PPU or what did we call it? Yeah, PPU instance PPU. Okay, PPU equals to PPU address, and now to the actual execute function we need to pass the ampersand runtime context here. So this is gonna pass the runtime context as a parameter, and which means the execute that the main function that we have now needs to also accept this as a parameter. So this becomes TNES runtime PTR. Yeah, this is where the type comes in. This just gets generated as it is, so there is no real value for it in the compiler. Okay, let's see if this works. Runtime context cannot convert runtime context to unsigned char star. Oh yeah, we didn't cast the types properly. Okay, the type def needs to be changed in the pipeline here. It's probably pipeline. Yeah, here is the one. So what's the type for these now? NES runtime context type. Yeah. So yeah, the function pointer that returns from the compiler needs to be typecasted in the right type, and that should make it work, I think. Yeah. It's compiled. Okay. Build NES compiler. Again, a segmentation fault. Let's debug this. Come on, I removed the debug flag. Too excited. Wait, I think I know why this is happening. No, I think it's just fine. No, I don't know what this is happening. Okay. Handle PPU store. The context is still 0. Why is the context 0? Let's look at it. Okay, it's null pointer. What is var23? It's easier if I just do this. var20. What is var20? Is equal to var13. Oh god, var13 is uninitialized. It does get this value here. Oh, we never set it inside the context. That's why it went wrong. Okay. Oh yeah. Okay. It's the execution context, runtime context, and daemon bit. Yeah, so it creates this here. This needs to also have it. and we added this here, right? NES context T. Emulator outage, yeah. Yeah, we added runtime CTX. Okay, so that means needs to be set. Add it to the constructor. Okay, so this becomes yeah, we forgot to copy it in one place. Oh, we also need to change the constructor call. Oh, okay. Okay, great. Now we are back to the same position where there's a jump to the invalid address. So now we properly emulate the PPU. But before we do any of that, I'm going to turn on optimizations again so it doesn't run slow. Yay, okay, so it's running and jumping to the wrong address, which is what was happening. Now we actually go to the PPU handle. Okay, so going back to the description for the two instructions that we have, PPU control and PPU status. So PPU control has 8 bits, VPHBSINN. The V is for NMI enable, non-maskable interrupts enable. PPU master slave, that is P. Sprite hide, background tile select, sprite tile select, increment mode, name table select. Okay, so it's a bunch of things we need to go through it very carefully. So controller, 2000, when you can only write to it, you apparently can never read from it, so that's good. Common in PPU CTRL, definition, PPU control register, access right, various flags controlling PPU operation. So this is actually easy. Whatever write comes in, we just store it inside the PPU. We don't need to do anything with, we don't need to interpret it right now. So since we are doing that before, so okay, let's first decode this address. This address is guaranteed to be between 2000 and 3 FFF, but we only have to look at the lower 3 bits. So what I'm gonna do is make some macros. Hash define PPU control 0x000. Actually 3 bits only, so let's actually just make it 0. Then we have PPU mask, hash define PPU mask 1, PPU status 2, OAM adder. What time is it? 12:24. Okay, we have an hour and a half. I have to actually rush exactly at 2 today. I have a lunch plan with a friend, so I have to run. PPU data, OAM data. What? Why is there one extra? You have 1, 2, 3, 4, 5, 6, 7, 8, 9. The 9 of. Oh no, this is a separate address. OAM DMA is a separate one. Great. So we'll use that differently. So, okay, so handle PPU load. If adder equals to OAM DMA, that handle the OAM DMA. Else it's guaranteed to be between 0x200 and 2 whatever 5. So we can just say switch on adder and 0x7. Only look at the lower bits, and now we can say is PPU control. This should never happen, so assert 0, assert false, invalid load on PPU control. Actually, I could just use a default in this case. Okay, so load is allowed on PPU mask. Is PPU mask allowed to be read? No, only write. Status is definitely readable, only readable. So okay, let's put PPU status, return PPU of status. We will change this later to compute the status properly, if that needs like some runtime state. There's a PPU status, and then we have OAM address is only write, OAM data is read and write. So OAM data return PPU. Okay, yeah, this is not going to be straightforward. It's going to be you have to look at some PPU memory, so that happens later. Okay, so OAM data return. Let's go back. Scroll is only write. 6 is also only write. Data is read write. So PPU data. It's going to be 0 again. The status will change as we go through it. Which also means we need an init PPU. We'll change this to whatever this is later. Okay, so this is fine. Default. Oh. So the compiler doesn't complain. Okay, this is fine, and now we need to have a similar case for handle PPU store. I don't know if OAM DMA is readable, writable. It's only write, so actually this, okay, there'll be an assert there. Okay, this goes away. None of these are actually right. OAM data and PPU data are read writable, right? Yeah. So for now, they're just gonna do return. Status is not writable, but others are. So PPU control. Just gonna make some state change in the PPU. We have to implement that first. It changes. So the PPU internally has an address that it's currently writing to, and this changes where to start writing from. And every time you write to the data, it moves it ahead by 1 byte. False is undeclared because obviously. So C. If I didn't save everything. Assert.h. Okay, expected semicolon before colon token 21. Why? Of course. Okay, multiple definitions of init PPU. What? Why is it in runtime.o? First defined here. Did I add it accidentally to the? Oh yeah, of course I added it to the header. Could make it static, but it's not the right way to do it. Great. Okay, it's still working the same way, but it's now reading from our status register. Now let's see what the status register is supposed to actually do. It has 3 bits, VSO. This register reflects the state of the various functions inside the PPU. It is often used for determining timings. To determine when the PPU has reached a given pixel of the screen, put an opaque, non-transparent pixel of sprite 0 there. Okay. So what are the values? The last 5 bits are always 0. It's good. Sorry, last 4 bits. It says dot PPU open bus returns the stale PPU bus contents. I guess that's never gonna be used. Sprite overflow. The intent was for this flag to be set whenever more than 8 sprite appears in the scan line, but a hardware bug causes the actual behavior to be more complicated and generate false positives as well as false negatives. This flag is set during sprite evaluation and cleared at .1, the second dot of the pre-render line. Sprite 0 hit when a non-zero pixel of sprite 0 overlaps a non-zero background pixel cleared at .1 of the pre-render line used for raster timing. Vertical blank has started. 0 not in vblank, 1 in vblank. So this is the bit that we actually were looking at. This is the one that this is the one that decides whether the status bit is positive or negative. Not in vblank, 1 in vblank. So technically we should be returning in vblank, but does that mean that the processor can only start in vblank? I think there's something wrong with our implementation too, because I think what this logic is supposed to do, if I understand the way the Super Mario Bros. ROM is written, it keeps on like looping till it goes to a vertical, till it gets out of vertical blank. So that's supposed to actually be a loop. I don't know why this is generating a jump to a invalid address. So let's check that. This means I need to dump more stuff out of the ROM. Okay, so here we are. So it does LDA ABS BPL relative, and the BPL relative I think this is just supposed to run in a loop. Like this BPL relative is not going to go to 7F92, it's actually supposed to go to 800D, actually 800A. So I think we're misinterpreting how the relative addresses are. Let's debug this. So when we have BPL, PC plus equals to get relative offset. So we can just print the relative offset here. BPL relative offset equals %d in this case, yeah, because it's a sign number. I want to check what we are interpreting it as and what it should be. Yeah, the BPL relative offset is 251. So what are the hex bytes? No, it's 251. Wait, why is it 251? That's not what. Okay, 251. So we need to figure out what that means. Bump up the font a little bit. Actually, let's go with this. Okay. We were debugging this the last time and we realized there's a mistake with it. So it's 251. The highest bit is 1, which means that the remaining bits need to be treated as a negative number. So this is a large number, right? Are we not supposed to treat this as... Is this 2's complement? Let's see what the 2's complement of this is. So the 2's complement would be 0, 0, 0, 0, 0, 1, 0, 0. And what is this in 4? So that makes it -4. Is that right? Is -4 supposed to give us the right answer? 800D -4. So 0x800D -4. 009. So it does jump here. TXS transfers X to, wait. Oh, it's supposed to jump from the current after this instruction. So 800D +1 -4. 800A. Yep, and goes to the load. I think we're just interpreting it wrong. Oh, this manual doesn't say it properly. Come on. Here it is. So relative offsets. This mode is used with branch on condition instructions. It is probably the mode you will use the most often. A 1 byte value is added to the program counter and the program contains execution from that address. The 1 byte number is treated as a sign number, that is, if bit 7 is 1, the number given by the bit 0 to 6 is negative. If bit 7 is 0, the number is positive. This enables the branch of 127 in either direction. So, but the example takes it as -913. It doesn't do it as a 2's complement. A long time ago I asked a question on NES Stack Overflow. It might be related to this, the wrong profile. Give me a second. Let's go to my profile. I had asked a question about NES. Maybe this was the same problem that I had run into. Can I not search for questions? I'm logged in, right? Why does it not let me search my questions? Okay. Yeah, sorry. Most of my questions these days are about templates. Was it on a different web? Maybe it was. Yeah. Was it a different community? Yeah. Indirect. This was something different. Man. Okay. NES or MOS 6502 relative addressing. I think I'm just decoding it wrong. Relative. Yeah, see, it says offset is a signed byte, so it can jump a maximum of 127 bytes forward or 128 bytes backward, which means it's a signed 2's complement. It's not what's it called? Signed bit representation. And I mean, they lied to me. This documentation lied to me. This is wrong. Okay, this example is also wrong. That's why it was all jumping. Okay, so to fix this, we need to change how relative addresses are decoded. Get relative offset. Okay, so this is not how this is supposed to be treated. I think what we can do is just interpret that as a signed char and cast it as integer. So I could just say return integer signed char star ampersand d. Huh? Yeah, just cast it as a signed char, return the integer value. Yeah, this should do it. Yeah, because we know that at least on our system we're using 2's complement. We could implement like a whole if condition and then swap the bytes, add 1 and so on, but I think this should work. There we go. Okay, see, now it runs. And it goes to 8008 and that returns 0. So this is not crashing anymore. Let's look at the code actually. This is gonna be interesting. I'm gonna clean all the scratch files. I'm gonna run this once. And okay, we have one C code. Perfect. Why does it return 0? Well, guess we'll find out. Hey, we have our while loop. Great, this is what we wanted. But what is this while loop for? No, this is not the while loop. What does it do inside this while loop? Takes the context, sets the registers, three two seven seven six, But it doesn't do anything inside this while loop. Var 12. This should needs to be a reference, man. It's just taking the same thing and copying it again and again. Fix that. What is this loop for? This is a sync out, so that's fine. 32776. Yeah, it's that first 8008. Let's see, why is it? But why does it? What is var 12? Var 12 is 32 shifted by 7. 32 is runtime load byte of 30, which is 8194. So that is 2002. Okay, so the jump is not loading it again. Maybe it's jumping to invalid address again. Okay, let's just compute how much back it is jumping, or what is the relative jump supposed to go to. So, oops, BPL again. It was BPL though, right? 8008. Yeah. Oh, there's an exit here. I see. Why is there an exit here? Oh, it's jumping to a wrong. It's jumping to the middle of the instruction. I think we messed up decoding again. Right, so 800D minus 4 should go to 8008, but sorry, 800. Yeah, I think it's just jumping to the wrong instruction. That's why it's putting an exit. That should be easy to fix. So BPL later offset is 251. Printf BPL jumping to okay, so now we'll see where it is trying to jump. I think it's just jumping to a wrong instruction, jumping in the middle of an instruction. Here we go. Yeah, it is jumping to 8008. That is wrong. So how is 251 interpreted? Just quickly try it out. Oh, not Java. Let's see. So unsigned char x equals to 251, and then the operation that we did, int offset equals cast to int star sign char star ampersand x, and then this should be -4, right? It's -5. Why is it -5? Why is it -5? Oh, if the highest bit is 1, you flip all the bits and you add 1, not just flip all the bits. So it should be 5 then. Let's go back to reading that relative thing. Relative address sequence is only for branch operations. The byte after the opcode is the branch offset. If the branch is taken, the new address will be the current PC plus the offset. The offset is a signed byte, so it can jump maximum 127 byte forward. Yeah, this is standard 2's complement. Yeah. So is it -5? And we were jumping from where? 800D. 800D minus 5 is gonna be 8008, but that is in the middle of an instruction. We don't want that. Should technically go to 800A, I think. Here, this is supposed to be a loop. Okay. We could check from my previous implementation again and just see where it is jumping. It's jumping to 8008 or 8009 or 800D. It's one of those values. It has to be one of those values. It could be that it's not supposed to continue. Like maybe that's the reason. Like these. So this PC plus equals to 2, and it actually gets out of the case. It adds 2. So maybe the PC has already gone ahead. Not supposed to. Let's try this. Yeah, we can check the and make sure that the implementation is correct later, but let's try this. Okay, yeah, now it's stuck in a loop, which is what it's supposed to do. So it's that those 2 bytes are maybe supposed to be added. I'm gonna quickly check this in the previous version. x86 translations, relative, yes, the relative branch. No, I don't remember Jack. Okay, here it is, BPL relative to move negative RAX. If it is this, then jump to instruction 10 end. Okay, otherwise do a relative branch. Moves the I think the only I'm confused about it. What does the PC point to? The PC points to the current instruction, or it points to the next instruction? That's the only thing I need to know. If it's the next instruction, then I think we are sorted. to worry about this. Oh God, what is this a reference? Okay, there it is. As the program counter itself is incremented during the instruction execution by 2, the effective address of the rank instruction must be within. Alright, fine, then we have to keep those things, which means all these will go away. Can clear this for now. Yeah, so we just increment and we don't actually continue. That was a mistake. What is this for? Oh, this is absolute. This is fine. This needs a jump. JSR jump to subroutine. Sets the PC and then it needs to jump. Okay, this is fine. These are okay. Okay, good. We're getting stuck in a loop now. Now we need to actually implement the PPU stuff to get out of that vertical blank. We could initialize the PPU to be out of the vertical blank by always setting the PPU status flag to be like to have 1 at the highest place. So let's just test that out. So in the init PPU, instead of setting PPU status to be this, we could do 0B1. Right? So that way it will have the highest bit set 1 and it will be out of vertical blank. And now it's stuck somewhere else. Hopefully. Or maybe it's just actually running the program loop now. The 100 follower. Thank you so much. I hope you enjoy what we are trying to do here. Yeah, so now the program is getting stuck in a loop, which is what is expected, because as the emulator runs, things just keep on executing. Nothing more is being compiled right now. I think the only way more things will be compiled is when the PPU actually changes some state, or like the code is waiting on something to happen, and that's not, we haven't implemented that yet, so those changes are not happening, which means the code is just busy waiting for it. But before we do that, before we start going into like the PPU implementation, let's just check if that loop is being generated properly this time. Okay, there we go. And great, so this has a check this time where it loads the byte first. Yeah, it loads the byte. Then, you know, I need to fix this context thing first. It's just making it unreadable. This just needs to be a reference. You don't want to assign it every time like a copy of this context is being made. No. Okay, let's see what this is. F59. Hey, what the hell? What? How did this happen? Okay, so var 13 should be used, right? What? Why is it? Huh? What does this even mean? I have to fix this. This needs to be a ptr ampersand 2. It was needs to capture it by reference. Okay, there we go. And now we have a nice clean little while loop, which loads the byte from this address 8194, then shifts it by 7, checks if that shifted value is true. Apologies about this. This is just an artifact of how build it works. So, but that's okay. Again, the working compiler can handle this, and this keeps on looping till this comes out. So in our case, this is gonna be fine because this loop we have returned like to made it to return 1, so this is fine. And then what is this doing? 8194 again loads the same status register. Is this the same code? Why did it produce the same loop twice? Something is different though. Why did it produce the same loop twice? It's gonna be the wrong behavior. Unless they have the same code twice, which is possible. Like to double make sure that it's coming out of it. This is annoying. There is one loop here, and then it should do SEI, CLE, LEA, STA, LEX. Oh no, these are just starting from the beginning again. Oh, sorry. We are at 800D, and then what's after D plus 2 is EF, 800F. Oh, it is the same thing. Yeah, okay. So there is a load again, and then there is a BPL again. Oh, great. Okay. My bad. So it has two jumps consecutively. We can check that we have a log from before, so we can just use that and see. Yeah, so here we go. For some reason, it has the loop twice in the code. I guess they just wanna double make sure that it's 1. Okay. So in our case, that's going to happen correctly. Okay, so we haven't made a mistake. It's just how it is implemented. Let's see what the rest of the code is. So we have those two loops, and then there's another loop here which does a bunch of things, and I'm assuming that it gets stuck in one of these loops. Great. We finally fixed that bug from last time. There's 2 reasons. So now that we have fixed this, I can sort of explain what happened. There were 2 causes as to why this code was running wrong. One was the address 20x2002 is not a normal address, which means it should return a different value from the PPU. And the other thing was wrong was the way we were decoding the relative offsets. The old manual that I was looking at said that it's if the highest bit is 1, then read the remaining bits as negative, which is what I was doing. And the example, in fact, talked about it too. But that's not how it's supposed to be. It's actually supposed to just be a signed integer. That's it, like a signed byte. If the first bit is 1, then it's a signed byte. Otherwise, it's a normal. I mean, I guess it's always a 2's complement. So that's what it was doing wrong. And the other thing was also, once we fixed that, we also had a small issue with having to add the 2 bytes for the jump, irrespective of whether we are taking the branch or not taking the branch. And that fixed the issue. So we have the loop correctly working now. You know what I'm going to do? I'm actually going to make something to debug this, in that for every instruction, I'm going to insert a runtime printf that says what instruction is currently executing. So we will know what loop is what we are stuck in. And this is very easy to do with Build It, because it's just inserting a runtime printf. And we already have a printf, I believe, somewhere. Yeah, we have a runtime printf. So we're just going to use that. So at the start of every instruction, once we have made sure it's in the thing, so we're just going to say, and we can remove this later, runtime printf executing we could do the whole thing, like we could actually print the opcode, instruction name, and everything, because these are just constants. But it's okay, we don't have to do that for now. Just let's print the addresses. Okay. We can comment this one out. Come on. Okay, so it's stuck in a loop of 90DE 9, sorry, DC D64. Okay, this is the loop it's stuck in. Okay, which is fine. Nothing is wrong with this. We can find where these instructions are by looking at the generated code and just figuring out what the loop is and what addresses it's loading and so on. What? This is the latest generated one. Oh, come on, these are not in hex. What is it? 90D4. $37076. 1076. I could change Build It to print it in hex, but that's okay. Okay, so this is the loop it's stuck in. Yeah. There is supposed to be a break on this, right? 76, 78, 80, 82, 84, 86, 87. Yeah, it's one of these instructions that it's getting stuck in. Is this the pattern? Yeah. So where is the break in this? There are 2 breaks. One is at 8.9 or 9.2. It's checking something to be 0. I'm guessing it must be reading something from the PPU again. What we can do is we can instrument the runtime to also print what addresses it's reading if it's a special address. Oh, we put it inside the header. Yeah, here it is. So def reading just to know what is it waiting to change. Wait, I think my makefile is wrong. Oh, includes only has the includes for the includes for the include directory. It should also have runtime includes included in it, because if the runtime headers are changing, the compiler also needs to be recompiled. Yep. Okay, let's see. Interesting. It's not stuck on any of those. So what could it be waiting on? It's literally not doing any loads. That seems... Is it even printing it ever? It is. Should be waiting on something. D4, D6, DC, DE, DF, E1, and then goes back to D4. Let's just look at what these instructions are. Have them decoded here. 90D4. Okay. So it compares CPX. What is CPX? Compare X as? Yeah, with 1. BNE relative 004. So D4, D6, then does DE. Okay. DF, E1, D4. Okay. Yeah, this is gonna get stuck in a loop forever because there's no load. Like, what is supposed to change? CPX, BNE, CPY, BCS, STA, DEY. I mean, there's a DVI. relative 4. Okay, so if x is not 1, okay, so it says compares x with 1, b and e relative 0, 0, 4. Yeah, so if it's not 1, it jumps 4 ahead, so d4 goes to d8. Okay, and then it compares cpy with 60 for some reason. Okay, and then bcs branch on carry set. Yeah, stay indirect 0006. So there is a store. Okay, let's see if the store is happening at least, or maybe the store is what is causing it. No, but how is it going to change control? Is a store and then decrement y and compare y with 0ff, and if it's there, then it jumps back to f1. It's not equal. Okay, so it is storing. No, it does read now. What? Why wasn't it printing before? Oh, sorry. Okay, so it just keeps on writing to a bunch of addresses. CFDE 200 in such weird ways. Oh, like just decrementing one by one, and then it will keep on doing it till it reaches FF. Will it reach FF? Let's see. It's possible that we have some issue with the wraparound. Oh boy, this is a long wrap. So, writing address equals. There we go. So it keeps on decrementing. BA9. Keep on going. Anyway, BA987654332. Yeah, it does go to 70FF. So it should make a different jump this time, because this is what it checks, right? CPY 0xFF and then not equal relative jump to F1. I mean, it should go outside then. It should go to 903. Yeah, this does a store and then decrements and compares, and that comparison should give equals, which means it should not take the jump and go to 90E3, but it never goes to 90E3. Okay, let's look at what the implementation for BNE is. I think this might be wrong. It looks right to me. Maybe the 0 flag is not set correctly on what? DEY. Instruction DEY. Register is equals to register y minus 1. Set n. Oh, we're looking at 0. Oof, output equals 0. No, that's not how it works, right? No, first we need to look at CPY. Loads the data, takes the register, set the lowest bit in the second byte before performing the subtraction. Oh, it does subtraction. Okay. So the lowest bit in the second byte before performing the subtraction. I have no clue what this is. Okay, so this is the same as subtraction, but doesn't set the accumulator. Okay, normally when you have a subtraction, you have an accumulator being set. Okay, what is this doing? Context.wireg, set the lowest bit in the second byte before performing the subtraction. So it says lowest bit, but it sets the high. Oh no, the result is a TNS word. So it first upcasts the register to be that. Okay, so it sets the highest bit, which is 1 shifted by 8. That is right. Yeah, res equals to res 1 shifted by 8. Okay, and then it subtracts the data from it. And the carry flag is then again checking if that bit is set or not. Okay, context.carry flag. Okay, but that's for the carry flag. The output is just 0xff. Yeah, just take the result and mask off the higher bits. So if it is ff and if you're comparing against ff, it should be 0. This is right. So why is set C not happening? I guess I just need to attach a debugger to this and step through this now. This is going to be painful. Guess I can do it. Oh yeah, I just have to yeah, I'll just compile it with debug so that I can put a breakpoint inside. Okay. Pipeline. Where's pipeline? Yeah, when it gets stuck in, we'll just look for it. Okay. What's the register mapping for? Wireg, because that's the one we are interested in right now. Must be var4, right? And check. Yep, var4. So now we just have to check. We have to stop when var4 is 0, 0, right? Okay, so it adds that's 49 to var4. Let's see what 49 is. 1792 is 70. Okay, so this is the address. Okay, what is var4 here now? 96, which is in hex. I can just, what am I doing? No, px, yes, 60. So that's 7x60. So what I'm just going to do now is wait for it to become 1. So let's say watch, no, break, where do you want to wait? Say 188, right? And then I forgot the syntax. I think it's just condition, right? Condition, yeah. Condition, breakpoint number. So breakpoint is 1. var4 equals 1. Continue. Okay. Great. Now I'm going to step through this one by one and see what happens. So we do next. So it goes here. This is 37086. So px 37086, which is 9D. Sorry, 09DE. And what is that instruction? (9)0D is DEY. Okay, this is actually implementing DEY now. Okay, so var4 equals to var4 minus 1. Next, so now if we do px var4, it is 0. Next, var4 equals 0. It's gonna set, and now there should be 3790df. What is 90df? It's comparison with y. If it's gonna still not work. 90E1, this one, the comparison is gonna go through and we're going to jump back. Okay, so it went back. 90D4, which is this. Wait, this time it's comparing x. I guess that's fine. D6 is this one. Okay. DC, which is this one. Okay, so now it's again ready to store y. And it has done the store to 070. Okay. And now there should be another decrement, which is 90DE. Yes, so that's going to be decrement. At this point, next instruction actually is 0xff. Now the comparison should return 0. Let's see what happens. df, which is comparison, right? Yeah, df is comparison. Okay, so var 55 equals to 255. This is what we are comparing against, and var 4 is also 255, so the comparison should be correct. Okay, great. Next, so we do var 56 equals to var 54. Next, and we set the highest bit, so var 56 is 511. Okay, and then we subtract, so we get 256, which is 1000, and then we shifted back by 8 to get the carry flag, which is fine. Okay, this is the carry flag. This is gonna give us the negation. Oh wait, no. Print var 57 should be 0 at this point. No, it's... Oh, we did OR when we should be doing AND. This is the mistake. Oh god. Okay. That should fix it. Okay. So CPY. Oh. We did make a mistake after all. This should be... We're taking the lower bits. It's gonna happen a bunch of places, I think. There's only CPX, CPY. There's also sub. SPC. Yeah, this does the same thing. God. This is ADC. This is also wrong. ASL. Arithmetic shift left is also wrong. Jesus. Masking the bits is hard, folks. This is jump on subroutine. What? I've done this everywhere. Taking the low bits, I've done OR. And my Spotify started. Comparison again wrong. Okay, this seems to be right now. Yeah, when trying to get the lower byte, I did an OR when I should be doing an AND. What? How did I make that mistake? Okay, and now it is finally jumping to an invalid address, which is supposed to happen, but let's stop printing garbage first. Okay, returning from address 90E6 function execution returned 1. What? Tried to jump to 1. But this time it did get out of our loop. So 90E1, then it went to 90E3, E4, E6, and then E6 is wrong. So let's see what E6 was. Yeah, so 90E1, E3, E6 is RTS. RTS is what? Return from subroutine. So it pops stuff off the stack and creates a return address out of it. Is it possible that my stack is corrupted? Let's look at RTS implementation. Oh, this is JSR RTS. This needs to be implemented like jump because the jump flag is read from the memory. Okay. So it loads low and high. SP equals to SP plus 2. Adder equals to high or low. Adder equals to adder plus 1. Sync regs out and print. So I think the adder is just coming out to be 0 for some reason. High. Oh yeah, this is the reason. you load it in a byte and then shift it by 8, obviously it's not gonna work. So this is needs to be word. Yeah, that should fix it. Yeah, we were shifting the higher bits by 8 when it's just a single byte value. That doesn't work. I was losing the higher bits. Still not correct though. Yes. The low doesn't need to be word. Shifting by 8 and then ORing with low. Still returns 1. Basically this whole thing becomes 0 for some reason. It thinks it stuff out. RTI also needs to be fixed, by the way. Should we check this? Yeah, so every time it does an RTS, it's going to tell us what address or what values it popped off the stack. Yeah, it popped 0, 0. Interesting. Where does it pop 0, 0? That's a bigger problem. What is the corresponding JSR for this? Yeah, this is wrong. No, this is fine. Low byte is PC and 0xFF. So this one is actually going to take the lower this time. Okay, let's just check what it is pushing. The corresponding jumper for this. JSR. And we can figure out from here why is it going wrong. If it is pushing 0, 0, then something is wrong here. Okay, so where is the corresponding JSR? JSR is, I mean, jump to subroutine is basically like a function call. Come on. 2D08. So then why is it popping stuff wrong? I think the stack pointer might have bugged. Oh. Okay, we can also print what values it is pushing at. this should be the same, right? And then RTS. What did I copy? I'm getting close to 2 p.m. I have to go. I'll try to fix this bug and then we'll close for today again. Okay, so RTS popping from FT and FE. That is absolutely wrong. Okay. Let's see what the corresponding GSR was. Yeah, it's F. The stack is initialized this way. FF and FE, but it's popping from FT and FE. So okay, so it should be FF and FE. Context.sp plus 1. Okay, I just have to check if the SP is updated properly. Okay, let's go to the GSR again. So the GSR, what does it do? It takes a low byte and the high byte, stores the low byte at the high byte at SP, and then low byte at SP minus 1, and then decrements the stack pointer by 2 because we have done 2 bytes. Okay, so now when you decrement it, it's pointing to the next location. So I guess when you do the reverse, you just increment SP by 2 first and then load from the same addresses. That might be an easier way to do this, right? Let's do the reverse first. Well, and low and high goes to SP and SP minus 1, is that right? The other way, okay. High goes to SP, low goes to SP minus 1. So low goes to SP minus 1. Low goes to minus 1. I think this should fix it. I think the stack push and stack pop wasn't implemented properly. Unless there's something in the middle that's changing the stack. FEFD. Okay. FEFF. Still wrong. GSR pushing at address FE and FF. But this one is popping from. No, this is fine. FE and FF. FE and FF, yeah, and FE and FF. Okay, so now the problem is that it's popping wrong values. So somewhere along the way the stack got corrupted. Did I initialize the stack pointer to the right value? Did they initialize the stack pointer to the right value? Is FE and FF the right place? I think registers are supposed to be uninitialized. There is a init code which does set up the stack by pointing it to ff. This is what like commonly used init code. Yeah, see the same code that we saw before. Blank wait. So they are doing the same thing. Our ff is pointing. I mean, it's customary to point. I guess it's convention to have the stack at ff and fe. So what is changing that? I guess we just need to put a watch point on that and see which instruction is causing that return address to get corrupted. It's going to be annoying because I think this is fine. We can do this. We can attach a debugger, put a breakpoint on the JSR, break, execute, yes, run. Okay. What is SP map to? Let's look at variable. So a var5. Okay. Here's what I'm gonna do. Watch. We're gonna check every change to SP. No, wait. SP is not gonna change. var5. Yeah. Oh wow, this is the slowest thing ever. Hardware watch points? What is happening? Why is this so slow? I put the watch point wrong? Okay, but here's what we wanted. Okay, so it has pushed 2D80 in it. Now we just need to see where these addresses are changing. So I'm going to remove all watch points. Okay, no watch points, good. I don't have any watch points. Now I'm going to check var0, which is var1, no. pp frame 2 print var0. That's our main buffer. Check var0 of 0xfe, which is 45. In hex, it's gonna be 2D, which is what we had pushed, great, and ff, which is 80. Okay, so now what we're going to do is going to put a watch point on the values that are getting corrupted. So which is both of them. So we could do watch var0 0xfe. Okay, I made a syntax error before. And then I'm also going to watch. This is a hardware watch point now. Great. 0xff. Continue. Here it is. Something is corrupting with a runtime store. And that instruction is 90dc. Let's see. Frame 1. Okay, there's a runtime store here from instruction GDB list more instructions. How do I no, I'm gonna see more code. I think they just list 10. Nope, let's just go to list 5. Oh, come on. Frame 1 GDB list window. Does anyone remember how do I increase the window for listing? List size, set list size. Okay. Here we go. So (90DC). I think this is one of our culprits. STAY indirect 006. But this was not supposed to write at FF, right? We are 51. Yeah, no, this is I see. Why? Print var 4 is 255. Print var 49 is 0. Oh, this might be wrong again. The shift might be wrong. Oh god. Yeah. What is this instruction again? STAY. Y indexed. Here's the Y index computation. This looks fine to me. Wait, why is it modulo FF? Oh, what? Is it zero base address? Should be modulo 256 or this. Oh god, I made a mistake here again. Modulo 255. Shifting the addresses completely. Yeah, modulo 255 doesn't make it correct. This I think should work. Nope, it's still jumping to the wrong address. Guess I'm gonna do this again. (800A). (90CC). Is this that subroutine? Yeah, FEF. Okay, great. Now watch 0 Wait, this is a different kind of an instruction. 90 DC. It's Y indexed. So why is Y index doing this? Okay. This is Y, which is 0. Zero, zero. So it's just loading 0, 0, zeros, which is just makes sense then. And then when you add var4 to it, which is ff, it's storing to address ff, which is wrong. Wasn't it supposed to be 7ff that it was storing to? We are at 2. Have to wrap up. Let's try to fix this quickly. It is storing to 0, 0. These 0, 0 is coming from. Wasn't it supposed to be 7f? 7, 0, 0, 0. Yeah, I think we just screwed up the whole address calculation for the stores. Oh wait, no, that was breaking out of the first loop. But it does break out of all the loops. I think it's supposed to clear everything except for the 0th page. But for some reason in our case, it's also clearing the 0th page. Yeah, it's... Okay, there's still some bug here, which is causing us to write to the wrong address. It's not supposed to clear the 0th page. Yeah, these all seem fine. Yeah. Okay. So they're using x and y to keep decrementing. Yeah, so there is a comparison here, right? Like if you say this comparison checks if x is 1. If it is 1, then it not equal, it goes there. Otherwise, it goes here. if relative 0002. Yeah, for the first page, it basically does this. If x reaches 1, if it is not equal to 1, then it goes here, here, and then stores y. Otherwise, it does compare y with 60 and only jumps. So for the rest, it just BCS relative 2. So a plus 2 is BC. No, but after 2. So DE. Yeah, so it just directly jumps. So without storing, it jumps. Okay, yeah. So if it is 1, it skips over 60 to 0, I'm supposing. Yeah. Oh, that was that sequence of writes then. But no special things for 0. Okay, we will debug this the next time. I think I know where the issue is. Yeah. All right. Thanks, folks. I'm gonna close here since we are at 2 p.m. This was fun. I don't know why the stream says 2 hours 40 minutes. We have been online for 3 hours. Not sure. Okay. We'll continue this the next time. I'll push these code changes. Let me just go to just talking. Yeah. I'll push the code changes. Try to debug a little bit on my side before I come online next time to make sure that I know what the issue is. We'll fix it online still. I won't fix it beforehand, but I'll try to at least debug where the issue is so we don't waste time debugging it. Yeah, and I'll upload these today's session again to YouTube, so you can watch it there if needed. Thanks. I'll see you next week.